Hello and welcome back. We are very glad to see you, and big thanks to all of you who have subscribed to our channel since our last video. Today we are going to learn all about RC filters, when and how to use them, and how to choose values for resistor and capacitor. So, let's get started. If you enjoy practical electronics tutorials like this one, please subscribe to the channel. Don't forget to like the video and enable notifications so you don't miss future projects. Thank you. By definition, resistor and capacitor in series makes RC circuit. It is almost identical to voltage divider circuit, where instead of two resistors in series, now we have a capacitor and a resistor. Depending which component is connected to the ground, we have low and high pass filters. For low pass filters the capacitor is connected to the ground, and for high pass filters, the resistor is connected to the ground. The word pass in this context refers to all the frequencies that pass unattenuated through the RC filter. Unattenuated means that they will pass through the filter without reduction in amplitude. The function of RC filter, as the name suggests, is to filter out the unwanted frequencies from the circuit. For both types of RC filters, the main parameter is their cutoff frequency. For low-pass filter, cutoff frequency parameter says that from that frequency and higher, signal will be attenuated, or simply put, the amplitude of the signal will be significantly reduced, and frequencies below cutoff frequency will pass unattenuated. Likewise, for high-pass filter all of the frequencies lower than cutoff frequency will be attenuated, or their amplitude significantly reduced, while all frequencies higher than cutoff frequency will pass through the filter without attenuation. In short, cutoff frequency is point from which high-pass filter passes frequencies, and for low-pass filter, the cutoff frequency is point from which filter stops to pass frequencies. As you might have guessed, the band and stop filters are a combination of high-pass and low-pass RC filter, which passes or blocks just certain range of frequencies. The formula for calculating cutoff frequency for all types of RC filter is the same, and it is displayed on the screen. We also need to emphasize that RC filters work only and only with AC signals. This dry theory and definitions can be a bit unappealing, so let's make things clearer by giving a real-life example. In speaker configuration, most commonly, you have front left and right speaker, and a subwoofer. Frequencies that subwoofer reproduces are below 300 Hz. So, if we want to split our audio signal, and send all frequencies below 300 Hz to a subwoofer, and all those above 300 Hz to left and right speakers, we need RC filters. We do this to improve quality of listening experience, since subwoofer is designed to reproduce low frequencies with higher fidelity than common speakers. Likewise, common speakers are designed in such way that they reproduce higher frequencies with higher fidelity, so it's a match made in heaven, as the saying goes. So, we are going to do the following. We will calculate values for resistor and capacitor, so that their cutoff frequency is exactly 300 Hz. First, we will feed one portion of our sound signal to low-pass RC filter, which will allow only frequencies below 300 Hz to pass with 100% of amplitude, whilst simultaneously attenuating all other frequencies and shrinking their amplitude to not more than 1% of original amplitude. We will feed output from low-pass RC filter to our subwoofer. Analog to this, remaining portion of our audio signal will be fed to high-pass RC filter, that will attenuate or shrink to 1% of original amplitude all frequencies below 300 Hz, and pass all higher frequencies with 100% of original amplitude. We will feed output from high-pass RC filter to our left and right speaker. In audio setups, this is how you get that famous 2.1 speaker configuration, 2 common speakers, left and right, and 1 subwoofer. Next, we have our band stop and band pass RC filters. As the name suggests, their function is to block or pass certain range of frequencies with 100% of original amplitude, while attenuating all remaining ones. Here, you need to calculate 2 cutoff frequencies. One for start cutoff frequency, and the other for stop cutoff frequency. This is how karaoke machines work. Band pass filter will pass human singing that usually ranges from 1 to 2000 Hz, and block all other frequencies. Likewise, stop band will block these exact same frequencies from original track, filtering out original singer, and replacing it with input from your microphone. Now, how do we implement RC filters in real-life scenarios? Let's take for example our NPN transistor amplifier from our previous video. Now, at first glance, capacitor C and resistor are two make high-pass filter, right? We feed input AC signal into capacitor C, and resistor R2 is connected to the ground, so by definition, these two components make high-pass RC filter. Well, this is where all the trouble and misunderstanding arise when learning about RC filters and amplifiers. Remember when we said that RC filters filter only AC signals? Here, we have to distinguish DC and AC components of the circuit, primarily, our 5 volts battery being major DC component, and out AC signal being out major AC component. Next, we have to distinguish what AC component sees. From AC signal's point of view, the 5 volts battery doesn't exist in the circuit. AC signal sees DC power source as very low impedance resistor, whose value can be safely disregarded. So, in short, for AC signal, the battery in the circuit doesn't exist, and represents closed circuit. So, from strictly AC point of view, we can erase battery entirely. Now, surprise surprise, from AC point of view, resistors R1 and R2 are no longer in series, but in parallel, as their respective terminals now share the same points, so we can redraw our circuit to match the new reality. Now, clearly, all three resistors, R1, R2, and RE are in parallel as well. Logical question is, why is not collector resistor in parallel as well? Transistors are designed in such way, that current can flow only from collector into transistor, then out of emitter terminal. So, by design, AC signal cannot travel upward from base into collector terminal. Also, if you have watched our previous videos, you know that there is some small parasitic current that can flow upward, from emitter to collector, called ICEO, collector to emitter leakage current, but it is very small and can be disregarded. So, with all that said, we can disregard collector resistor entirely, as we can safely pretend that AC signal doesn't see it. In reality it does, but its significance is negligible. We can safely erase collector resistor from the picture. So, we are now left with following configuration. Now, there is only one more job to do, and that is to solve problem of voltage drop across base emitter junction. If you have watched our videos, you know that there is 0.7 volts of voltage drop across base emitter junction. We have also explained and demonstrated how this voltage drop can be represented with equivalency diode, and then this diode can be substituted with equivalency resistor, called RE. This internal resistor should not be confused with emitter limiting resistor with a similar name. There is one more for the book of idiotic naming schemes in electronics. To distinguish these two resistors, current limiting resistor is marked with capital R, and internal base emitter equivalency resistor is marked with small r. So, finally, this is what our AC signal sees. It sees resistors R1 and R2 in parallel, and all that is paralleled with resistors RE, and emitter current limiting resistor with same name, who are in series. Now, there is problem with resistor RE, we do not know its value. Determining value of this resistor requires book on its own. We will use following formula to calculate its value. Also, value of this resistor is dynamic, and changes with presence of AC signal, so, our final formula for calculating equivalency resistor which our AC signal sees is displayed on the screen, where beta is current gain of transistor, with no AC signal present. For simplicity of calculation, beta is assumed to be 100. So, where were we? We were trying to calculate values for capacitor and resistor for 300 Hz cutoff frequency for our amplifier. If we take schematic for amplifier from our previous video, and plug in all the numbers, we get that equivalency resistor that our AC signal sees is around 900 ohms. By utilizing formula for cutoff frequency calculation, and expressing formula to calculate capacitance, we get that we need approximately 0.6 microfarad capacitor. So, if we plug in 0.6 microfarad capacitor in our circuit, our amplifier will amplify all signals from 300 Hz and above, while all below 300 Hz will be significantly attenuated. Now, this is all very highly complicated and complex to calculate. Is there a way that we can simplify all this gobbledygook? Now, in previous videos, explaining and learning about voltage dividers, and resistors in parallel, we have learned that if 10 times bigger resistor is placed in parallel with smaller one, the bigger resistor can be disregarded with acceptable margin of error. So, we are going to do exactly that. Since emitter resistor Re is 10 kiloohms, and it is much bigger than resistor R2, which is 1.2 kiloohms, we are going to disregard it. Also, we are totally going to disregard emitter resistor Re, internal base emitter equivalency resistor, and we are going to calculate equivalency resistance for what AC signal sees, by just using resistors R1 and R2 in parallel. So, if we do the math we get that equivalency resistor, by just using resistors R1 and R2 equals 912 ohms. Calculating capacitance value for capacitor C, using 912 ohms equivalency resistance, gives us 0.58 microfarads. This is all within 10% margin of error that is acceptable in any electronics calculation. So, we can safely assume that equivalency resistance that AC signal sees are two resistors R1 and R2 in parallel. This simplifies our calculation for cutoff frequency tremendously, and introduces negligible error in calculus. Next item of business is solving the dilemma on how to choose values for capacitor and resistor. Is the combination of smaller capacitor and bigger resistor better, or is it the other way around? Well, there is no definitive answer, but there are some general recommendations in which direction to go. If you have cheap capacitors that you have obtained from Far East online sellers, truth is that those capacitors are of the lowest quality and pretty inconsistent value of capacitance. For example, a ubiquitous 104 capacitor, with 0.1 microfarad capacitance, can vary anywhere from 50 to 150 microfarads. This is pretty big and unacceptable margin of error. For smaller capacitors, the situation worsens. On the other hand, even cheapest resistors have smaller margin of error, around 1 to 5% of their declared value. So, logic dictates that you will get better result by using larger capacitor, with far less discrepancy in its capacitance from declared value, and smaller resistor that already has a smaller discrepancy in declared resistance. Furthermore, variable resistors are way cheaper than variable capacitors, so if the money is factor, then choice is clear and obvious. Our recommendation, use whatever you have on hand, it will work. Now, for those of you who are familiar with passive RC filters, you might wonder why we did not mention attenuation in decibels, and those famous logarithmic scales for voltage drops. Simply, they really are not that important and they just introduce confusion in what is already pretty complex subject. But, for all those of you who want to know every possible single detail, here are the graphs. So, how should you read this? In an ideal RC filter, jump from cutoff frequency to pass frequency is instantaneous, and every frequency that is filtered out has zero amplitude, and every frequency that has passed has 100% of original amplitude. Of course, we have learned so far that there is nothing ever ideal in electronic circuits, so why should filters be an exception? They are not. Of course, real-life RC filters have some slope between cutoff and pass frequencies. Furthermore, frequencies that are filtered out do not have zero amplitude, their amplitude diminishes slowly over several hundreds of hertz both left and right from calculated cutoff frequency. Likewise, frequencies that are passed, also do not have 100% of original amplitude, as there is intrinsic loss in voltage drops across both resistors and capacitors, as both of those are not an ideal components as well. Now, there is a way to mitigate this problem. If you want as steepest as possible slope for the frequency response for your RC filter, use as big capacitor as you can get, and smallest resistor that fits the calculation for cutoff frequency, and your RC frequency response graph will be almost identical to an ideal RC filter. You are welcome. We hope that you have enjoyed this video as much as we enjoyed making it. We would appreciate your feedback very much. Please, before you leave, show your appreciation by liking this video, leaving a comment, sharing it, and please subscribe to the channel. Thank you, and see you next time. Bye.